My name is Roger Williams, a curriculum developer and instructor with Solar Energy International. Let's keep going. So our learning objectives for this lesson will be, you'll be able to define and list the characteristics of series and parallel circuits. We'll show you how you can calculate different values for current, voltage, and power depending on the configurations. We'll also review the application of series and parallel connections to ensure system compatibility. Of course, we are working with electricity, so we have our warning here. PV installation work is for qualified personnel only. At the bottom of the slide, you see the definition of a qualified person from the National Electrical Code. I'll let you go ahead and read this and just pause for a minute. So all in all, you got to get more training, and SEI certainly promotes the safe working practices and wants to make sure everyone is safe doing this work. Okay, so on to series connections, and some of you may have heard of series and parallel before, but we're going to go through what in fact this means. Here we have our two modules. You see it's VOC, or it's open circuit voltage, and ISC, or it's short circuit current. And first we would check a module and see, yep, there we go. We're measuring the VOC of that particular module, and we have 39.5. And when we make a series connection, it's the negative from one module to the positive from another. So there we've made our series connection. And now when we take our voltmeter and look, we get 79 volts. And in fact, with series connections, the voltage is additive. So we have 39.5 plus 39.5 to get our 79 volts open circuit of this situation. And the current remains the same throughout all parts of the circuit. So there we have our ISC of 9.6 amps. That doesn't change from making this series connection. Again, the series connection is the positive to the negative, or negative to positive, however you want to say it. And then these unused or open leads become what we call the positive and negative home runs. That's where you would connect your wires to go back to your next component. So that is a very simple diagram of one series connection made, and we would call that, or several modules in series forms a PV source circuit, or sometimes you'll hear us say a series string. The NEC says PV source circuit. So very simply, that's the basics of series connections. And here's an example in a flashlight. So we know that we fill some batteries into our flashlight, and those are actually all series connections in this example. Our batteries are 1.5 volts, and they have 4 amp hours each. But again, those are all series connections. And what happens when we put things in series? The voltage adds. So what would the voltage be for this particular flashlight? Well, we have 1.5 volts plus 1.5 plus 1.5 plus 1.5. That equals 6 volts for this particular flashlight. And how many amp hours are contained in that small battery system? Well, in fact, remember, in series, the current or the amp hours do not add up. They remain the same. So this would be a 6-volt flashlight that would have 4 amp hours of time that it could run. We have this in here as an example because most folks are used to seeing a flashlight, and batteries are direct current. They're DC, they have positive and negative, just like a PV module. And so now we can look at the IV curves of PV cells in series. So we have one cell that's indicated by that blue curve. Maybe it's got about 6 amps and almost zero point 0.6 volts at VOC. Okay, so that's one cell, the blue curve. Now, within the module, cells are connected in series to each other. Positive to negative, positive to negative, positive to negative, and on and on. And so that voltage adds up in the module. The voltage of adding another cell in series shows up as that red curve. The current of the two cells stays the same, but notice that the voltage has now doubled. Now we have a VOC close to 1.1. So that is how PV modules are made. All the individual cells typically are in series within the PV module. So we'll show you how we build that up. There are those two cells with the positive to negative series connection, and our curves barely show up. But then when you put a whole column, we build that voltage. Then we put in another column. We just keep building that voltage for the whole module, and the black curve becomes the PV module's IV curve. Note now we have our VOC that's a little over 36 volts. So, so that's series connections of cells within a PV module. Now I'll introduce parallel connections. Here we have our modules. Now this time we're really going to look at the VMP and IMP of this particular system. So we're going to wire positive to positive and negative to negative. Note there are no series connections here between two modules. So we have positive to positive that go to that combiner box, we'll call it, and we have negative to negative where each module has its own circuit to that combiner box. And then in the combiner box is where the parallel connection actually happens. So once we connect these two individual circuits to the inverter, whatever device that is, that begins to operate. And now in parallel, the current is what's added. So here we have an operating system. We measure the current for one circuit. We get 9.1 amps. And now we go and measure the current after the two circuits are paralleled, and we see that we get 18.2 amps. And so that is the critical thing with parallel connections, is that the current is additive. And in fact, the voltage remains the same throughout this system. Here we have a VMP of 31 volts. That's the module's VMP. It does not get added there because it's in parallel with the other module. And here we're going to introduce another term. We have the PV source circuits are really the individual circuit from one module or from a group of modules. And after those source circuits get paralleled in that combiner box, that forms a PV output circuit. And in this case, that PV output circuit goes between the parallel connections and the device there, the next component. We're measuring 18.2 amps on the PV output circuit. And so the positive and negative wires would leave that combiner box or where they get paralleled, and they go on to the next component, which we're showing is that device with the system operating. And in this case, we are operating. We have our VMP of 31 volts. We have a output circuit of 18.2 amps. That equals about 564 watts. So that is only parallel connections. No, there are no series connections in this example. So now we'll go, look, we bought a bigger flashlight this time, and now we're going to fill it with those same batteries. So we build up our voltage. We have our four 1.5 volt batteries in series, and then we're going to add four more of the exact same battery in series. And note at the top and bottom is where we make our positive to positive and our negative to negative parallel connections. So now, what would the voltage be for this flashlight? Once again, we add up the series connections, and that is only four batteries. 1.5, 1.5, plus 1.5, plus 1.5. So we still have a 6-volt battery, but how many amp hours does this hold? So each series string of batteries is 4 amp hours, and we parallel those battery strings, so now we get 8 amp hours. So again, that's an example to show you how we do this with batteries almost in our everyday lives. And now we're going to show IV curves of PV modules in series and parallel. Now remember, we have one module. There's its IV curve. And all of these modules are the exact same module. They have the same voltage and current parameters. So we put one in series. Now we double that voltage, add a couple more, and there is one PV source circuit. That's the IV curve for that entire group of 5 modules. Now we're going to add another group of 5 in parallel, negative to negative, positive to positive. You see how we build that. We kind of stack that curve on top of the other one, and now the voltage stays the same, but the current has doubled. We went from 6 amps to 12 amps, and now we're going to add a third PV source circuit in parallel. You see our final IV curve are these 3 PV source circuits, and now that they're in parallel, our current goes up to almost, or a little over 18 amps. So again, we put modules in series to build up the voltage, and then we can connect them in parallel to build up the amount of current that we want in a particular system. This is the end of part 1 to our lesson on series and parallel. Please join me for part 2 when you're ready. Thanks.